Hello my students. Today our topic is diet bread. Diet bread is a part of ecology through which we can understand the diet preferences or many a times diet overlapping between two species. Diet is an essential part for living. Each and every organism has some preferences for a particular diet, and this diet is composed of the resources means the food types which are available in that particular habitat. So when we study diet of a particular organism or a species, we actually see from which habitat the organism comes or in which habitat it thrives. A food which is dominant in a particular habitat may be the preferred food of the particular organisms. So diet bread gives a direct indication of food types and the range of preferences of the organism for a particular diet. This diet may be a single diet or may be a range of diets. So this diet bread we are going to discuss today, and also we will learn how to calculate the diet bread in some organisms, mainly the fishes. So in a very standard way, you can say it refers essentially to a diversity of food resources used and shown by any organisms or group of organisms. And here you can see the food resources means, if you talk about planktonic food, you may have a number of planktons. So these are the food resources. If you have zooplanktonic food, you may have a number of zooplanktons. So zooplankton is a food resources. So food resources is a very flexible term depending on your requirement or the way you want to analyze. You can use this term food resources. So when we have a diet bread of an organism which is very wide, we can say the food habit is general or the organism is a generalist organism. But when we have a very narrow diet bread, we can say it is a specialist diet bread, organism with a specialist diet bread. So these two differences you can later analyze to conserve the species, to understand the habitat or the different requirement of the species for other different purposes. And many a times the diet bread are calculated on a range of from 0 to 10. So here it is shown 0 to 8. 10 is a very ideological condition. So 0 to 10 may be a range of diet bread of organisms. So it may be anywhere else between 1.5 to 7 or maybe 5, 6 to 8. So whatever. So this index we are going to follow some index. So these indices may give some ranges which may fall within a scale 0 to 8 or 0 to 10. We can easily understand what is the diet bread. When it is 10 means the organism has a full choice, a wide range of diet bread. It has no specific selection. But when it comes to 1 or 2, we can say it may have some kind of selections. And a number of diet breads are available in different books you will find, but we are going to discuss only few of them. Say for example, one of the popular diet bread is Levin's diet bread. This is the Levin's diet bread. Then again, you can remember that earlier classes we have studied Shannon-Weiner diversity index. This can also be used as a measure of diet bread. This is Shannon-Weiner index, and there is one more, Halbert index and Smith index. In these two indices, Levin's and Shannon-Weiner indices, the gut content or the food available in the gut or food available that consumed by the organism is considered. This P means Ni by N, as you know, Ni by n, as you know, this n is the food that is consumed by the organisms, and this n is the total number of organisms that is consumed by the particular organism under study. The p, where the Levin's this p denotes, the same p is here, it is ni by n. But you can see here in this case Halberts and Smith, many a times what we miss it, number of food organisms available in the environment and number of food organisms consumed by the organism. There are two resources. One is available in the environment, and second is which is found in the gut of the organism. So in case of second case, this is available in the organism environment, you can find this as a p, you know, that is already consumed by the organisms. Here in case of Halbert and Smith, this is as a, which denotes the organisms which are available in the environment. So let us see how these different indices behave. That is some data we have for 4 fishes, and this data I am keeping some variations. You can see for the fish A, the gut content of the fish may have different variations of food. All are zooplankton. The resource state is zooplankton. So you can see fish A, there are a number of food items, and they are not uniform, 25, 4, 10, 8, 6, etc. Similarly, in case of fish B, you can see there are also variations, but here the number of food items are more than the fish A. When 25 is in case of zooplankton 1, here it is 36. So in all cases, this number is higher than the fish A. So we will see how the indices behave in this case. Again, in case of fish C, you can see all the food items are found equally, means there is no variation, they are evenly distributed in the gut. And in case of fish D, you can see zooplankton 1 is very highest number, that is dominant, this abundance is very high, and rest of the items are only negligible amount, that is 1 only. So we will see how these indices behave in this case also. Now in case of fish A, if we calculate Levin's diet rate, that is ni by n, this total n is 64. So if you divide 25, this is 25 by 64, what you are getting? 0.39. So this similarly you have to divide 6 by 64, 8 by 64, 10 by 64. So all 64 you have to divide, then what you get? 0.08, 0.09, 0.06. And remember, summation of pi, it becomes always 1. This pi summation always becomes 1. Now as per the requirement of Levin's diet rate, it is pi or pj. J is the food item, j food item. So or you can say if your I means I food item. So this is pi or pj, whatever you say, it is squared in this case. So pi square or pj square, whatever, you will get 0.39 square is 0.15. So you can square all these pi's, then you will get these numbers. And finally summation of pi's squares, summation, this is the summation. So summation you do, all you add up, this is summation, and that summation is, you can see how you can say formula, this is summation you got, then 1 divided by the summation, 0.22, this is 0.22, it becomes 4.55. So the problem is that, like Shannon winner, here there is no upper limit. 4.55, whether it is more or less, you cannot say, because you don't know what is the upper limit. Similarly, you can calculate for fish B also. You can say total number is 311, 311. So 36 by 311 you do, just you divide it and you'll get 0.12, and similarly you will get all this data and finally it is 1.0, and square of this data will come down like this: 0.01, 0.01, 0.02, so finally 0.15. You might have seen I have taken two digits after decimal points. So when we will calculate these figures, we should always take a particular limit, that is I am taking 2 digits. So all 2 digits number I am calculating and rounding the numbers if it is 5 or above 5. So there also similarly you do the same thing, that is 1 divided by 0.15, it is becoming 6.67. Here also we cannot say whether it is higher or lower. Remember, although in the previous slide we got it is 4.55 and now we are getting it 6.67, we cannot say it is high or low because these numbers are different. These numbers are different. So depending on this number, this figure changes. So we need a scale. Before that, let us go to the fish C. You can see what is the speciality in fish C. Here the food items are evenly distributed, means all food items are equally eaten by the fish C. Then the question comes that when it is like that, all these food items are equally distributed, evenly distributed, then the resources become this index become maximum, highest. So we can see here to all equally distributed, then you are getting this number 0.14 and again 1.0, it is 0.14 and it is 7.14 finally. If it happens that these are not equally distributed, what would be the result? You can see this is fish D, where one item is very dominant, that is zooplankton 1. So others are almost negligible. Total items 175, you can make the fraction, that is 1.0, and similarly you can go for squaring these numbers and you'll get the numbers coming up like this, and finally you sum up all these squared figures, it is 0.93. So 1 divided by 0.93 comes as 1.08. Here you cannot compare because in all cases these numbers are different. That is why when you go for this formula, there is a difficulty that we cannot understand what is the upper limit. Although we now know that when any one item is very much dominant or two items are very much dominant, then the index goes low, it reduces. But when all items are evenly distributed, then it becomes the highest one. This highest number may be different for different food items. That is why there is we need a scale between 0.1 or any other scale, standardized scale within two limits, lower limit and upper limit. How to do that? So this is what standardizing the niche bread, or I told you that niche bread is not, it is diet bread of Levin's diet bread. So Levin's diet bread is BA, which is standardized diet bread, and this is the unstandardized diet bread. So B minus 1 and N minus 1. So N is total number of counts. So here this range becomes 0 to 1. So this is how the standardization done in case of Levin's diet bread. So now you, after standardizing, you can say this is N minus 1, 6, because we had total 7 numbers of counts, items, species total. You can you can go back and see total 7, 1, 2, 3, 4, 5, 6, 7. So this 7 we can take N minus 1 means this is 6, and this was the calculated B for fish A, 4.55, and B minus 1 means 3.55. So BA comes as 0.59, N minus 1 by B minus 1. So it comes as 0.59. This N is small a, small n. Okay. So this N minus 1 minus B minus 1 is equal to 0.59. And you can represent it in terms of percentage also. In all cases, you can do the same thing, 0.94. And you can here you can see the when all items are evenly distributed, it becomes 1.02, which is equivalent to 100%. So it is the maximum value of the index. And when you go down to fish D, which is having a very uneven distribution, only zooplankton 1 is dominant, there you can see 0.01, which is almost equal to 0%. So this way the Leibniz-Nisbet rate is calculated. In the first case, we need to calculate the B, then we have to standardize it using this formula BA, like this I have shown in the table, and finally we can express it in terms of percentage. Now here you can see the comparison of these figures. See, the fish A, fish B and fish C is the highest, it is 100%, and it was fish B was having the maximum number, you can remember 36, 30, like this it was having, and this was these numbers were the total abundance were lower, less than the fish B. So that is why the figure comes around 60, 59%, and fish D was 0. So there is no any kind of bar diagram we can see here. So this way you can compare the different fishes or different organisms for their diet breaths using Leibniz diet breath measures. And another one, as you know, Shannon-Weiner index. This is what H bar is equal minus summation of Pj log Pj. And what is Pj? It is Nj by N. This is also similar with a fraction of the total, Z item divided by total item. Here you can see the fish A, where the same numbers we can consider, and Ni by N, this is also same Pi, the fraction 25 divided by 64. Same way we can proceed. We can have 0.39, 0.09, 0.13, 0.16 and so on, and finally we can get 1.0. But here we have to find out log Pi. This log Pi is what? This is this Pi you have got from this column, this cell. Now we find out the log of this one. It is minus 0.41. Similar way you can find out all other numbers, which is log Pi, Pi, J, K, whatever the species. So now you can see here the Pi, this is the Pi and this is log Pi. Say for example for zooplankton 1, Pi 0.39 and log Pi minus 0.41. Now these two are multiplied. The product is 0.16 minus 0.16. So these two are multiplied and a product is written here, and for each case zooplankton 2 also we can multiply them, and this is the product, and all the results are you can note down here. And finally this Pi into log Pi, this product for each species are summed up. This summation of all this Pi and log Pi is minus 0.75. And you can see the formula, there is a negative sign, this is negative sign, summation of Pi log Pi, this particular expression Pi log Pi. So what we are giving here? Minus, so minus 0.75, it is 0.75. Now similar to the Leibniz, there is no upper limit. We cannot say 0.75 is higher value or lower value. For that there is a way in case of Shannon-Weiner index. We need to find out the maximum expected Shannon index, this H bar maximum, it is known as H max. H max means maximum expected Shannon index. It is calculated as log S. S means the richness, how many species are there. So there are total 7 species. So it is log S equal log 7. It comes is equal to 0.85. Now we can calculate the evenness by dividing H by H max. H means this is the H 0.75 and H max is 0.85. So these two are the main figures we have to use for finding evenness. One is H, this H which we have already calculated from this table, and second is H max, which is H max, which is log S. Now you found it 0.89, and this is ranging between 0 to 1. This evenness, it ranges between 0 to 1. So 0.89 means it is almost very 90, 0.9. So you can write it as 90% also, or you can write this, if you want to be very specific, you can write 89%, no problem. So this way you can find the evenness, and this can be used as a measure of diet bread for the fish species or any organisms. We can follow the same procedure in case of fish B. Here you can see the items are, these items, the abundance is higher than the previous table, that is fish A. So how it behaves, you can see there. Similar way we can follow. The total number is divided by this individual number, that is 0.12, 0.10, 0.14, like this. So the fractions are again converted to log values. It is coming in minus 0.94, 1.02, 0.84, all these negative values. And here it is the product of these two columns, minus 0.11, and similarly all the products. Now you can sum up, minus 0.83. So the the Shannon index is 0.83. Similarly, we can find out the H max, which is same for the fish B also, because we are considering the same table. Total 7 species are there, so it is 0.85. Now you can see here evenness H by H max, where 0.83 and 0.85, when we the 0.83 is divided by 0.85, we are getting 0.99, which, so it is when the more numbers are eaten up, or you can record from the gut, you can find the Shannon index also increasing. And here also you can see deviation or variations are very low, not very as the previous table. You can see the previous table, it was 25, 5, it is 5 and 6. The variation is very high, but here in this case the variation is not very high. So there is the increment in the evenness. In case of fish C, where we have the items evenly distributed, all are 25 in numbers. This we can calculate with a similar way. That is 0.14 you are getting, 0.85 you are getting, so minus 0.12. So all numbers are same. Now you sum up minus 0.85. So minus 0.85, if you find out the Shannon index, it is 0.85, and you have 0.85 as the highest Shannon index, that is H max, already we know. And if you find out the evenness, it is becoming 1.0. So since all are evenly distributed, it is obviously going to be 1.0, and we have got that one. In case of fish D, you can see that is that the one only species, that's zooplankton 1, is highly dominant, 169 numbers, and rest of the species are very low, 1 each. So there the total number of the product, that is pi into log pi, this product is 0.09, and in that case Shannon index is also plus 0.09. And this is H max. It is same in the previous 3 cases, as you have seen fish A, B, C. Here also it is 0.85, and evenness you will find it is 0.108, which is very, very low. So you can represent them in a graph this way. You have to represent H as well as the E, means the Shannon index as well as its evenness, and all the figures you have to put down, and that graph you can draw for the evenness. So this graph may not have any upper limit, but in case of evenness the upper limit is 1. This is the 1 you can see on y-axis, the upper limit. So there you can easily compare the species which are having almost evenly distributed food items, or which are having very low food items. and thereby you can understand that which species or which organism has wider diet breadth in terms of Levin's index, in terms of Shannon's index. So this is about the Shannon-Wiener index. Now coming down to Halbert's index. As I told you that in many cases we ignore the number of organisms available in the environment. In previous two cases, Levin's and Shannon, we have only considered the organisms which are available in the gut or that is consumed by the organism. But we ignore the organisms which are available in the environment. Any organism, it takes or it consumes food from the environment only. If the food is available in the environment, it may take the food. As I told you in the first beginning of the class, that the number of organisms or if the abundance of a particular resource is very high in the environment, there is a chance that the organism will prefer to take that particular organism as a food. So there is an impact, there is a proportionate relationship that if A is very high, P may also be very high, or you can say AJ is very high, PJ may also be very high. May not be true in all cases, but this is, you can say, a hypothesis. So what is PJ? As we have understood earlier, PJ is the fraction of items in a diet that are of food category J. So summation of P is always 1.0. And AJ is also similar definition we can put, the fraction of total available resources consisting of resource J. That is also summation of AJ is 1.0. And this here B ranges, this is Halbert's B, it ranges from 1 by n into 1.0. 1 by n is the lowest, 1 is the highest. Yes, the Halbert's Nisbet can be standardized as B dash A. So BA, you know that 1 divided by summation of PJ P square by AJ, PJ square by AJ. So this is what the B. And how to find out, calculate the BA? You can find here, this is the expression, same expression here. That means it is B dash, this is to 1, minus A mean, means the minimum of A, divided by 1 minus A mean. And when you do this, it becomes within 0 to 1.0 range. Literally, you may not find any difference between these two and the B dash and BA. But just to put within the range of 0 to 1.0, we need to convert it to B dash A. This is the table, the same table we have taken for fish A. Now you know that how nj by n we have calculated, pj square you know how we have calculated. Similarly, A is now the resources in the environment. This zooplankton 1, which is consumed by the organism, 25 items, and which is available in the environment, 30 items. And remember, it is not zooplankton literally or hypothetically, it is impossible that when there are 30 items are available and it has taken 25 items. What we do sampling. We go for random sampling of guts as well as random sampling of the water. So when we sample in the gut, we go for counting the organisms, and we find that 25 organisms per ml of food content collected from the gut. Similarly, from water, when we sample the zooplankton, there also we calculate the number of zooplankton or abundance of zooplankton. We find that 30 zooplankton per ml of water in the water body. So this is compared here. And similarly 6 and 10, 8 and 10, and literally, and there are always a higher number of A compared to P, because you know that the fish or the organism has to collect the resources from the environment, and that is why environment must have a higher number of organisms so that it will get this number. It cannot be that environment has 6 numbers of organisms and it is consuming 10 numbers of organisms. It cannot be done. It cannot be possible. So what happens? We always find the higher number of organisms means a value is always higher than the p value for a particular species. Now similar to p, where we have calculated pj, nj by n, which is pj, here we are calculating kj by k, the total of this one, which is k, and kj is the individual species. This is kj by k equal aj. So we are getting this fraction, the proportion we are getting for respective species. Now this is as per the formula. What we have to do, pj into aj, sorry, pj divided by aj. So this is we can do by dividing this pj whole square divided by aj whole square. Now you are getting 0.45. So this is, you can go for this, you can go for all the species, and finally you are getting 1.05. This is a summation of all these numbers. This is the figure you are getting here. In this case we are getting, this is summation of p square j divided by aj. This is what we are getting, 1.05. As per the formula, we have to divide 1 by this 1.05. 1 divided by 1.05. What we are getting, 0.95. Now convert it to the standardized Hilbert's diet bread. So here a mean, this a mean is not there. Here it comes a mean. So a mean is what? The a mean comes, you can see this is 0.07. So 0.07 is the a mean. This goes 0.07. This is 0.07. Here will come 0.07. 0.07. So 0.07. If you just subtract from here, it will become 0.88 divided by 0.93. So the ratio comes 0.95. So it is within 0.0 to 1, within this scale. This is scale. Now going to fish B, where this number, item numbers are higher than the previous number. You can see the numbers also very high in this case. There you can calculate, this is 1.01 similar way, and this is divided 1.01 similar way, and we got 0.99 as a B dash. So the BA, the standardized Hilbert diet bread is coming at 0.9 divided by 0.9. Subtracted, we have to subtract 0.9 from 0.99. Where it is, this is 90 is the lowest number, a mean. So this is coming 1 minus 0.09, 0.90 and 0.91. This is 0.99. So it is obviously highest. Now let us go to C. There you can see the 25 in all cases, and we have considered the number also equally available. So here you can see this 1.0. If we follow all the norms, all the calculations, we are getting 1.0. So this is clear that the number, when it is evenly distributed, it is the highest number, since the range 0 to 1 is the highest number. And in case of fish D, where one species has the abundance over the other organisms, other species, there it behaves 0.88. So you can see this Hilbert's diet bread is less sensitive to the rarest organisms, whereas it is very highly sensitive to the evenly distributed organisms. That is one of the drawback of Hilbert's diet bread, that when the number of organisms are high in case of only one species and others are very low, it hardly shows the numbers lower or smaller numbers, that is nearing to 0. So it is less sensitive to the rarest organisms. These organisms are not counted in this case. It is ignoring these organisms. Also maximum calculations are dominated by 0.83 and 1.12, which is coming 1.13. See, all figures are almost 0. It is coming 1.13 because there are some decimal figures coming up 1.13, but it's not very different from 1.12. So this 1.13 is giving us 0.88, which is retained here in after standardization. So 0.88 compared to this number is not very low. It should have been 0.2, 0.3 like this. So it is not very sensitive to the rarest organisms. So Halvard diet bread index, if we compare, you can see the numbers. Fish A, it is second one is within the scale 0 to 1. First one is without the scale. So fish B you can see, and fish C is very idealistic position, and fish D it is 0.88. Although it is not exactly showing the lowest number, but still comparatively smaller than rest of the fishes. Now coming to the Smith diet bread. Smith diet bread is almost similar to Halbert's diet bread, but here the expression is little bit different. But the parameters, that is Pj and Aj, these are similar. Pj is a fraction of items in a diet data of food category J. Aj also proportion of total available resources consisting of resource J. So these are the fractions. But we need to find the square root of the product of the Pj and Aj. Then you have to sum up. And you will find it's very surprising that this Smith diet bread will also show the same result as the Halbert's diet bread. Here in the first case you can see fish A it is calculated the same similar way, Pj, then Aj, then here Pj into Aj. These two are the figures we have to multiply, product of Pj and Aj. Then the square root of Pj and Aj is 0.36. In all cases we have to follow the same procedure. Then we will find these numbers, and finally you sum up these square root numbers, that is 0.993. So there is no other procedure, you can directly write 0.993. And you can go for the fish B. Here also you can see the same procedure, that is Pj Aj, that is multiplied, then square root, and you come down, that is 0.998. Then come to C, where the numbers are evenly distributed, and same table you have followed. Here also we got 1.0, that is the highest number. And you come to the lowest number D, that is 169, and others are only 1 available. Then there you found 0.95. So if you compare these two indices, that is the Smith index and the Halvard, you can see the first one, fish A, it is 993, then you are getting a difference in third decimal. So it is not very sensitive for the variation among the groups. You know, the first case you get the variations. This is see 25, 6, 8, 10, 5, 6, 8. Variations are there. The highest figure is 25 and lowest figure is 4. But in the second case, it is highest figure is 65 and lowest figure is 30. So there is a difference between this variation. The variation is here is very low, smaller compared to this fish A. So these variations are reflected in case of Halvard, but in case of Smith diet bread, these are not reflected. If you take the first two digits after decimal, you will find 99%. But if you consider only third digit, then you get the difference 3 and 8. So that is the problem with Smith index. But in case of even distribution, you are getting 1.0. And fish D, here you can see, although it was 0.88, but in this case, that is the Smith index, we got 0.95, which is very high compared to the distribution we have seen in that particular table. So this is what we have learned from the all these indices, and these are the indices we are using now for understanding the diet bread of species wherever possible. Although there are many other methods are there, but these are commonly used in studies and research purpose. In the next class, we will understand the diet overlap, and I think this class will help you to understand the diet overlap between two organisms.